Good morning. My name is Ignacio Hidalgo. I'm going to present work titled Short and Medium-Term Blood Glucose Prediction using multi-objective grammatical evolution that have been developed at the Universidad Complutense de Madrid and Universidad Rey Juan Carlos in Spain. In this paper, we presented a research for investigating the benefits of applying a multi-objective approach for solving the problem of model the glucose level in blood diabetes patients by symbolic regression and using a multi-objective grammatical evolution approach. So for this, in this presentation, I will follow the next outline. First, I will give you a brief introduction about what is the diabetes. Since the main objective of the paper is to investigate what is the benefit of the multi-objective approach, I will give you just 2 points, 2 ideas about the concept of multi-objective optimization. I will describe the problem, how we deal with it, and the details of the implementation. Then I show you experimental results focusing mainly in the comparison of grammatical evolution with the multi-objective grammatical evolution. And then I will give 2 conclusions of the paper. So first, what is the diabetes mellitus? It's a group of diseases that are characterized by a high level of blood glucose levels. And the cause is due to or a problem in the production of the insulin or a problem in the effects of the insulin. So we have mainly 2 types of diabetes. Diabetes type 1, where the body is not able to produce insulin, and this is about the 10% of the people who suffer diabetes. But this is probably the most dangerous and the most serious, because they need to control since the early ages the glucose and to deal with the disease. And the other one is the most usual, not the most popular, but the most usual, the type 2 diabetes that is usually produces after the 50s due to a sedentary life and the problems with other diseases. This is a real global problem. More than 400 million people suffer diabetes all around the world. It's probably one of the highest problems, not at now, but the highest problems in the future, near future. So the patients suffering diabetes need to control the blood glucose level, because as the insulin is not acting on the body, the glucose level in the blood are high. But also when they are eating or making exercise, the levels of glucose can go up and down to dangerous levels. So in order to avoid not only long-term complications like retinopathy or cardiopathy, etc., but also short-term complications, what the patients want to maintain or need to maintain is the level of glucose on a healthy range. This is no usually attaining range. The better, the higher the time in the levels from 70 to 180 milligrams per deciliter is the better. What we want to do is to help the diabetic to manage this situation. How? Well, what we will do is to prepare predictive models that make an idea of how the glucose is going to evolve in the close horizon time. Well, so in this paper, as I told you, we are going to apply a multi-objective approach. Let me first, please, to give you some ideas about multi-objective optimization. Just to comfort, when we deal with a multi-objective approach, that means that instead of using just one objective for guiding our evolutionary algorithm, we are using more than one objective. And in this case, what happens is that instead of having a point in an optimal representation, what we have is another concept that a solution is better to another one only if and only if is better for all the objectives we are dealing with. For example, in the figure of the left here, you have three solutions of a space representation of the solution. F1 is the first objective, and F2 is the second objective. So if we represent the compromise of each solution with both objectives, we can have this kind of representation. In this representation, we can see that solution P3 is supposing that we are minimizing both objectives. The solution P3 is worse than P1 and P2 for both objectives because P1 is lower in F1 and F2. And the same happens with P2 and P3. So in this case, we say that solutions P1 and P2 dominates P3. Okay. This is very important because, for example, solution P2 is better in the objective of P1. Sorry, in the objective of F1 is better than P1 because it's lower, but it's worse because this objective is higher than P1. So now the concept is a bit changing because what is the best solution, P1 or P2? I mean, we cannot say only depending on the characteristics of the problem solver or the indication of the fabrication process or whatever. So in this case, the new concept is that instead of looking for just one solution, we are looking for a group of solutions that have or that compose the Pareto front, which is the set of all the best solutions for a problem. In the graph, in the figure of the right, you can see a representation of the Pareto front with all the non-dominated solutions that are dominating the rest of solutions. Another important thing is that we can also have some invisible spaces due to one objective is contradictory with the other. So we can have a part of the search space where we cannot reach with an algorithm just because when one of the objectives increase, the other one go down and so on. But in this problem, please remember this figure for the end of the presentation because we reach the total optima in some of the cases. Okay, so coming back to the insulin recommendation, well, what we want to do is to construct, as a general project, an insulin carbohydrates recommendation tool in order to maintain healthy levels of blood glucose and the next time horizon age, healthy levels in the tenon range. So we change a bit the problem, and instead of looking for a recommendation, we try to evaluate different possibilities. So we construct predictive models for evaluating those recommendations and try to predict the glucose problem. Why? How? Using grammatical evolution, which is a kind of genetic programming well known in this conference, and using also the well-known non-dominated sorting genetic algorithm of DEB. So our predictive model should use information that we can collect in standard daily conditions. For this, we use data from patients, retrospective data from patients wearing first a monitor system, a continuous glucose monitoring system. Then wearing also an insulin infuser device for putting the insulin on the body, also both from Medtronic. And then we complete this information with notes of estimated carbohydrates taken by each patient. This work we present here was made some time ago. We passed several phases. So now there are several approximations. Here I just mentioning a list of a set of them. Mostly those that we put in the paper. There are several approximations in our group, most of them using grammatical evolution and machine learning techniques. And then there are also groups that were inspired in our work using hybrid models for different steps or different situations in the day, breakfast, lunch, and dinner, but using only synthetic data from a simulator. And there are also other approximations from people from the community of the evolutionary computation. Recently, the works by DeFalco using a GP induction for telemedicine. So the main objective is not to look for just better solution, just to know if the multi-objective approach could benefit the solutions. So we solve by a symbolic regression problem with all the data we collected. We made new features and new variables, and with this we tried to solve 4 different problems for 4 different time horizons: 30 minutes, 60 minutes, 90, and 120. With this, we look for a prediction of glucose in this time horizon with a set of features you can see here that correspond with the historical data, and using 2 objectives. On one hand, the root mean square error, which is usual for minimizing the error, and then an ad-hoc fitness function that we developed specifically for this work. We explain in the next slide. And here you can see that we have all the historical data. For example, glucose T minus 90 correspond to the glucose in the interval of 90 minutes ago, and so on. And you can see also that we have some information of the insulin in the time horizon and the carbohydrates in the time horizon. Remember that we changed the problem as a prediction of the glucose, but what we want is to evaluate a dupla of insulin carbohydrates recommendations. So the fitness functions we use is the root mean square error, the usual equation here. And the other one, what is most specific for this work, is the Clarke Error Grid function we implement here. The Clarke Error Grid is a grid where we represent the predictions versus the actual values. And we divide the grid in 5 zones depending on the severity of the mispredictions. So as the level of the letter increases, the misprediction is more dangerous. So what we try is to minimize the predictions in the zones C, D, and E that are the most dangerous for the patient, because we will do a change in the treatment that will be bad for the patient, provoking bad effects, even the death. So with this, we construct a fitness functions that account the number of points on each of the zones we want to avoid, that is C, D, and E, and we increase the penalization, let's say the value of the fitness function, as we increase the number of points on each zone. That is, with the points on C counts 1, on D 10, and on E 100. So the fitness function tries to reach the minimum number of points. So when we get a value of F Clarke of 0, that means that all the predictions are in zone A and B. And in this case, we also can reach a minimum point when we have a 0 error and a point in the Clarke Error Grid, a prediction with all the points in the zones A and B on Clarke Error Grid. So let's go now. The description of the grammar we use. This is the same that we use in previous work. You can look at the bibliography. It's just a grammar for using grammatical evolution. Grammatical evolution is a kind of genetic programming that make use of a grammar to decode the individuals. And in the grammar, we can direct the expression we want to obtain or we want to allow in the production model. So in this case, we are constructing a set of expressions that are composed mainly of variables from carbohydrates, from insulins, and from glucose, the historical data we saw in the general expression. And we use just 3 operators and no complicated operation, just for checking the grammatical evolution in the same conditions, the multi-objective approach in the same conditions of the previous work. So with this, we apply to a set of individuals, in this case, a real data set from 10 patients that are characterized by this information. The main information, as I told you, is the training range. You can say that, sorry, here the training range is a bit low. And we can see here also that the average value of glucose in some of the patient is a bit high. So let's go to the experimental result. In this figure, we can see a representation of in the Pareto space that is representing the root mean square error versus the F Clarke, the number of points in C, D, and E of the solutions. Each point, each dot is a representation of the value of the objective for a solution. And we compare here in the same figure the grammatical evolution with the multi-objective grammatical evolution for different time horizons: 30 minutes, 60 minutes, 90, and 120. And here, in this case, we are representing the patient 2, but we have similar results for most of the patients. What we can see here is that, for example, with the multi-objective approach, we are dominating all the solutions of the grammatical evolution without multi-objective approach, which is basically the objective of our research. And also here for 60, 90, and 120. This is a patient 2. There are some patients where the grammatical evolution sometimes obtain a better value, but in general, we can say that we can obtain non-dominated solution when using multi-objective grammatical evolution. Another interesting view of the results is this. Here we are seeing the same figure, but all the time horizons in the same figure. On the figures in the left, we are seeing the grammatical evolution, and in the other, on the left and the right, sorry, we see the multi-objective approach. And for patient 1, in the up the figure, we can see, for example, one of the things I told you In this case, with the grammatical evolution, we don't reach to a minimum point, but with the multi-objective approach, all the solutions reach to the optimal points for this patient. Probably will be because this patient has a better control of the disease on the glucose levels. And in the other case, what we can see here is, for example, in the patient 5, although the solutions in the grammatical evolution space are quite similar in quality, although we obtain more solution because the multi-objective approach for some on the horizon, but there are some points at the multi-objective grammatical evolution. For example, this one here near 70, where we reach a very good point with a reduced number of points in the zone, in the dangerous zones. This is the advantage of the multi-objective approach. We can obtain a whole set of solutions, and then we can select the most appropriate for the problem we are dealing with. And another view of this solution is represented here in this last figure I'm presenting you. And in this figure, we present the solutions for the multi-objective approach in the right, and from the grammatical evolution in the left. For all the folders and all the faults in the cross-validation process, and for one patient. Of course, we obtain again more solution with the multi-objective approach because we are obtaining the Pareto front. We are searching from the Pareto front instead of just 1 point. So here we can see all the solutions in the Pareto front. You can see in the figure of the upper for multi-objective, for example, where we can see very good the Pareto fronts we obtained for some of the faults. And also we can see in the down figure that again there are self-faults where we reach a very good points as a compromise of the root mean square error and the number of points. For example, this is very important in the interpretation of the results because although this solution has a higher root mean square error, is better in this case, not in the concept of Pareto front, of course, than the other solution because the dangerous prediction are reduced to a very low number. So with this, we finish the presentation. Well, we have also in the paper some comparison of the results in terms of the number of points, the percentage of prediction for each zones. This is an average, so it's not so representative. And as I told you, it's not the main objective of this work. So in this paper, we investigated the benefits and drawbacks of a multi-objective implementation of grammatical evolution for constructing model of glucose. We implemented a grammatical evolution combined with a NSGA-II algorithm, and using the root mean square error and a function based on the Clarke Error Grid. And results show that the multi-objective approach can obtain better models for reducing the number of predictions in the most dangerous zones for some of the patients. So could be a good approach for this. As I told you, this work was developed some months ago, and we published better results in a place of computing in December. Finally, this work has been supported by Fundación Eugenio Rodríguez Pascual in Spain, the Spanish Minister of Innovation, Science and Universities, and the Madrid regional government by 2 grants. So thank you, and I open you for questions.